Greetings to all. The concept to explain today is about loss distributions. So as an introduction, loss distribution concern of insurance companies for the understanding of claims data. So actuaries need to model both the frequency and severity of losses in claims. It is assumed that claims data are positively skewed. Now, some concerns of insurers is that if the claims is greater than a certain level, they go for reinsurance, and if the claim is less than a certain level, then it becomes a deductible or an excess. So in this presentation we are going to explain about loss distribution, about exponential distribution, gamma distribution, Pareto distribution, Weibull distribution, Burr distribution, and log normal distribution. So considering the exponential distribution, so we consider a random variable with the following cumulative and density function. So the exponential function has very tractable mathematical functions, but its disadvantage is that its density is monotone decreasing as shown here. So you can find the probability distribution, density function, and the cumulative density function. The mean and variance is 1 upon beta, and the variance is 1 upon beta square. We shall now move to the derivation of mean and the variance. We need first the probability density function and the cumulative density function. So the mean and variance are found by the method of moment generating function m theta. So the moment generating function is defined by the integral of e power x theta times fx, integrating between limits 0 and infinity. So when you integrate, you take the beta out, you will soon find that the MGF is b over b minus theta. So the mean of the exponential distribution is given by mean is the first differentiation of the MGF with respect to theta, and you set the theta to 0. So you get the mean to be 1 upon beta. For expectation of x square, you differentiate twice the MGF, and you set your theta to be 0, and you get 2 upon beta square. Now you can easily find the variance by expectation of x square minus expectation of x to the square. So now I'm going to show you an alternative method. It is going through the Laplace transform. So a Laplace transform of the cumulative density function, usually you integrate e power exponential power minus st times fx, and you integrate it, but here I have used a Laplace transform table where it gives the Laplace transform of exponential of minus beta x is beta, which is this constant here, over beta plus t. You take the first derivative of the Laplace transform, and you also find the second derivative of the Laplace transform to be these two equations here. And as you can see, the marginal generating function in general has this equation. So minus 1 to the power of k times the partial derivative with respect to k of the Laplace transform by dt to the power of k, and you set your t to be equal to 0. So you can easily show that the first MGF is 1 over beta and the second one is 2 over beta squared. So you get the general formula of an exponential the general formula of the MGF of an exponential distribution to be k factorial over beta power k. Okay, now let's have a look at the graph of an exponential distribution function. So to graph the exponential distribution, I'm using MATLAB. Here is a graph. So when the beta is at 0.5, I have a blue line here. When it is a big beta, quite big beta, which is 5, you can see that the exponential function gets more down. And here the red line is for a beta of 1. So what you see is as your beta increases, the tailing also increases. So this is the So now we come to the gamma distribution. You have a probability density function given below. So fx equal to beta power alpha over gamma alpha times x power alpha minus 1 and times exponential of minus beta x. So the condition for a gamma distribution is that your alpha should be greater than 0. What happens when alpha equal to 1? So when alpha equal to 1, you have a gamma alpha equal to 0 factorial, which is 1. And this will become x power 0, which is 1. And you're left with beta power 1 times exponential of minus beta x, which is the exponential of beta. So the expectation of x for a gamma distribution is given by alpha over beta, and the variance is alpha over beta square. So something about the gamma distribution is that if x follows gamma of alpha and beta, this would imply that 2x would follow the chi-square distribution with 2 alpha degrees of freedom. Now I'm going to show you the Laplace transform of the gamma distribution to derive the mean and the variance. So for the gamma distribution, I've already told you about what happens when alpha equal to 1, but when beta equal to 1, then you have the gamma of alpha x would be, by definition, would be given as this. Take the cumulative density function is just the integral of small f of x dx with limits 0 and x. So this gamma function here is known as the incomplete gamma function. Now by definition you can prove that n factorial is the gamma of n plus 1. There's an interesting video using the Feynman integration and Laplace transform by flammable knots. If you want to know the derivation, I suggest you have a look at the video. And then the Laplace transform of the gamma function can be proved to be beta over beta plus t power alpha. So therefore you use this equation above here, where you use this definition here. The moment generating function is defined as minus 1 power k times the kf partial derivative of Laplace transform over the kf partial derivative of t. So therefore you just differentiate your Laplace transform first, and you replace t to be equal to 0. You find the second partial derivative, and you can easily find the moment generating function. You can see that it will follow the pattern of over gamma of alpha plus k over gamma of alpha times beta power k. Then you can derive the mean and the variance. Okay, so let's have a look at the gamma. So now I have drawn the gamma distribution graph. So you can find that when alpha equal to 3 and beta equal to 2, you have a blue shaped curve here. When as alpha increases and beta decreases, so basically when alpha is increasing, you will see that the tail of the gamma distribution, the right tail, gets decreased, is less than when alpha is bigger. Another feature of the gamma distribution is that as alpha increases, here I've taken alpha to be 100, it gets closer to a normal distribution. Now we come to the Pareto distribution. So for the Pareto distribution, it's an assumption that if x follows exponential of 1 upon beta and that y follows the gamma distribution of alpha and beta, then we have a x condition on y will follow a Pareto distribution. So in this example here, we note the probability density function, the cumulative density function, and the mean and variance. So note that the Pareto distribution has fat tails. So the Pareto distribution doesn't have a Laplace transform. So therefore you derive the mean by if you're finding exponential of x, you integrate x fx dx, integrating between limits x between limits 0 and x. Okay, so now we're gonna consider the Pareto densities in the graph. Okay, for the Pareto distribution, there's a strong thick black line is for an alpha of 0.5 and a beta of 2. Weibull distribution. So the Weibull distribution also does not have a closed form solution for its Laplacian. So we could have f of x, that is a probability density function to be described as shown, and the probability density function to be shown here. That's the marginal. So a condition of Weibull distribution is that your tau here has to be greater than 0. So you'll notice that when tau equal to 1, what you have is you have an exponential distribution. When tau is equal to 1. When tau is greater than 1, when tau is greater than 1, 2 here, so you see that the graph is positively skewed, tilting to the right. So as tau increases even more, you have a symmetrical shape. And then here I've taken tau to be 0.5, so which is less than 1. So when it is less than 1, the tail is higher, and then the tail is heavier to an exponential, and is higher than the Pareto. Now for the Weibull distribution, so why do we use the Weibull distribution is because it offers greater flexibility for a heavily tailed distribution, okay, compared to the Pareto distribution. So if y follows the Pareto distribution, then y power 1 over tau follows the Weibull distribution. Okay, so you have a probability density function and the cumulative density function. The condition is that x should be greater than 0. So for the Weibull distribution here, this thick black line is for alpha equal to 0.5, beta equal to 2, and tau of 1.5. So the dotted line is alpha of 0.5, beta of 0.5, and tau equal to 5. So here, what you have alpha equal to 2, beta equal to 1, and tau equal to 0.5. So you see that's similar for the Pareto distribution. When you have a tau of less than 1, a value of tau which is less than 1, you get your graph to be a little bit heavier than the exponential, the Weibull distribution. So now we come to what's the log normal distribution. So we already know the normal distribution, which is a symmetric bell-shaped curve with parameters mean and sigma square. You have the probability density function of the normal distribution given as shown here. So now I'm gonna prove the PDF of the log normal distribution, which is shown here, but we're gonna move to its derivation. The log normal distribution. So given x follows normal distribution, we have mean mu and variance sigma square. So letting y equal to e power x, this will become x equal to log of y. So when I find the cumulative density function of y, I'll have probability of big Y being less than or equal to small y. So I substitute my y with e power x, so that would be probability of x being less than log of y, which is simply the probability density function of log of y. Now, having to find the probability density function, okay, when I find the cumulative density function of y, this is just a so therefore the probability density function of y will be the derivative of the cumulative density function here. So I derive this here, which is I take the derivative of log of y, 1 over y, and you differentiate this f of x log of y, which is f of y log of y, and differentiating with respect to x. Then I move to, I get f of y log of y here. I have the y outside my cumulative density function, and I get this to be equal here. Probability density function of a log normal distribution. So this process is often described as a Cobb-Douglas law. Now to find the log normal distribution, the cumulative density function, you use phi of log y minus mu over sigma, which is the square root of this thing here. And where phi is the standard normal, then and you find the moment generating function mk of y power k. So y is e power x, so you get e power kx, and which is equal to the moment generating function of xk with respect to x. So the moment generating function of x is mu plus sigma square over 2. With the k parameter here, it becomes exponential of mu k plus sigma square k square over 2. So you can find the expectation of y. You can find the expectation of y, so this is y here, and the variance of y. So some side notes. So as seen, there has been no closed form solution for Laplacian, for Boole and Pareto distribution. We find that the gamma distribution is wide skewed and approaches a null distribution in the limit as alpha goes to infinity. So the gamma law has tractable properties and is useful in creating other distributions, but by itself it is rarely reasonable for modeling claim sizes. So that is how we use Pareto distribution, Weibull distribution, and all of it has been shown here. If you enjoy this video, give it a like. Don't forget to share and subscribe to my channel. I hope we meet again soon.